say that you have some overall reaction in which A turns into C. Now, you might have only information, though, about the equilibrium constants for A turning into B and then B turning into C. Well, you can find the equilibrium constant for A turning into C because the equilibrium constant for a reaction is equal to the products of the equilibrium constants for its constituent reactions, the reactions which add up to that desired reaction, as you can see written here. This is because you might say, hey, what's the equilibrium constant for this overall reaction? Well, it's the concentration of our product C over the concentration of our reactant A. Now, this is equal to the equilibrium constant for our first reaction here, B over A. Okay, so equilibrium constant of the first reaction, which is B over A. And that times the equilibrium constant for the second reaction, C over B. And you can see that the equilibrium constant for our desired reaction is equal to the product of the equilibrium constants for the two reactions which sum to give the overall reaction. Okay, so as an example of this, what is the equilibrium constant for the dissociation of carbonic acid, where it releases 2 protons and leaves carbonate? So how often does that occur compared to, say, certain individual reactions in which carbonic acid releases just 1 proton, and then the bicarbonate that remains might release another proton to leave carbonate? So you can find the equilibrium constant for this overall process where we release 2 protons by finding the equilibrium constant for each of these summative reactions. Being that these 2 reactions add up to our overall reaction, we can multiply the equilibrium constants of those 2 reactions to find the equilibrium constant of this overall reaction. The equilibrium constant for the overall reaction is the multiple of Ka1 and Ka2. Note that this first reaction, where we have the first ionization of an acid, of a polyprotic acid, that might have some significant value, 10 to the negative 7. And it's increasingly difficult to release further protons, and so here we have an even smaller equilibrium constant. Even more rarely does this reaction occur. But in order to release 2 protons from what you start with, well, that's quite unlikely. It's the multiple of negative 7 and negative 11, negative 17. All right, so a more difficult problem, we can build up to that by talking about these couple factors. Now, for a reaction in which A turns into B, the equilibrium constant is equal to B over A. But what if you were to take the inverse of this reaction? What if you were to flip this reaction? Well, that would ultimately require that you take the reciprocal of the equilibrium constant of the original reaction. By taking a look where you flip this reaction to give B goes into A, the equilibrium constant of that is A over B. Now this is actually the reciprocal of B over A. So A over B is equal to the reciprocal of B over A, or equilibrium constant is equal to the reciprocal of the flipped reaction equilibrium constant. So flipping a reaction inverts the equilibrium constant. And then also, what if you were to double the amounts of reactant and product in a reaction? How would that affect the equilibrium constant? Take a case in which A turns into B. So the equilibrium constant for that is B over A. But what if you double the concentrations of both of these reactants and products? Then the equilibrium constant is B squared over A squared, which is the same as B over A times B over A, which is K prime times K prime. So we can see that the equilibrium constant for this reaction is the equilibrium constant of its constituents reaction squared. Doubling a reaction's coefficients squares the equilibrium constant. What if you were to triple the amounts of everything? Then your k would be equal to k prime cubed. What if you were to take a halving of the coefficients of all your reactants and products? Then your equilibrium constant would be equal to the square root of the equilibrium constant of the original reaction. So using these two facts about doubling and flipping a reaction, we can do a problem which is a lot like Hess's law, which we saw back in thermochemistry. So say I'd like for us to determine the equilibrium constant for this reaction in which two sulfur dioxides are combusted to provide two sulfur trioxides. Now, all that you are given is that sulfur reacts with oxygen to give sulfur dioxide, and it has an equilibrium constant of 4.2 times 10 to the 52. And also you're given that two sulfurs are combusted with three oxygens to give two sulfur trioxides. And that has an equilibrium constant of 9.8 times 10 to the 128. So in order to determine the equilibrium constant for this reaction, just like in Hess's law, you need to be able to add up the constituent reaction to give the overall desired reaction. So in this case, where we have two sulfur dioxides on the left, ultimately we're going to need two sulfur dioxides on the left as well when we're adding up our reactions. Now, currently, you can see that we have, if we just added up these two reactions that were given, we would have sulfur dioxide on the right side of the equation, but we need two sulfur dioxides on the left. And so we'll need to flip this overall reaction, but also in order to get two sulfur dioxides on the left, we need to double the amounts of everything in that equation as well. And so by flipping and doubling that reaction, we get 2 SO2 gives 2 sulfur plus 2 O2. Now, by flipping and by doubling the amounts of everything in that reaction, we will have to take the reciprocal of our original equilibrium constant, and we'll have to square it as well. Now, it really doesn't matter what order you do this, whether you take the reciprocal then you square, or you square then you take the reciprocal. It doesn't matter. It'll give you the same value. But you can see here now that adding up these two reactions, one in which we just kind of created and one which was provided to you, we see that we do get the two sulfur dioxides on the left just like we need. Now, we need two sulfur trioxides on the right, and that's how we have it. And we need one oxygen gas on the left. Now, having two oxygen gases on the right and three oxygen gases on the left, these ultimately will cancel out in that two oxygens will be removed from the right, two will be removed from the left, leaving one O2 on the left. So we have two SO2s on the left like we need, we have one O2 on the left like we need, we have two SO3s on the right like we need. So being that we can add up this and that reaction to give this one, we can multiply these two equilibrium constants to give the equilibrium constant of our desired reaction. So doing that, we get 5.5 times 10 to the 25. Thanks for watching, guys.